The sky this month, okay, January the 14th to February the 12th of 2022. Let's go. Okay, first of all, highlights. Well, I want to talk a bit about the James Webb Telescope deployment, because that's certainly what's in the news. And I just want to kind of relate that to where it is in the sky. And even if we are unlikely to ever be able to see it, I just kind of want to know where it is. And the planets, of course. We'll just take a look at a few of the appearances of the planets throughout the month. So let's go look at the James Webb orbit. So here you have a simple diagram that indicates roughly where the James Webb Telescope is. So we have the Earth, and just 570 kilometers from it, the Hubble, that's the Hubble telescope, orbited very close to the Earth. And then we have the Moon, 384,000 kilometers away. And then 1.5 million kilometers away, we have the Webb telescope. Just to complete that, there's also the Sun. And the Sun is 150 million kilometers that away. And here, this L2 is the Lagrange point number 2. And it turns out that all Lagrange points, but this one in particular is sort of a gravitational sweet spot. And we'll take a look at that a little bit more later. Okay, so why place the Webb telescope there? Well, it turns out it's located so that the Sun, the Earth, and the Moon are always roughly in the same direction. And that makes shielding a lot simpler, shielding the telescope from the heat. And that is certainly an issue, because on the hot side of this satellite, the temperature is going to be roughly 85 degrees Celsius, which is hot enough to brew coffee. But on the telescope side, it's designed to take it down to minus 225 degrees Celsius, which is the temperature at which oxygen freezes solid. So big difference between the two sides of the heat shield. So it's really imperative that everything be simplified. So this is a picture of the Webb telescope oriented in the same way that you saw in the diagram I just showed you, to shelter the scope from the Earth. So it turns out that the infrared sensor sees heat. So it was just like we were talking about, Richard was talking about with his CMOS sensor. The Webb telescope is designed particularly to see infrared. And so because the detector sees heat, you don't want any stray heat around from the equipment or from the Sun or the Moon or the Earth. So it turns out there are 5 layers of thin foil that screen the scope. You can see those layers there stretched out. It really gives you an idea of what a Rube Goldberg piece of equipment that the Webb telescope really is. It's just amazingly kind of weird contraption designed to do its specialty well. So it shelters, these foils shelter heat from the Sun, the Moon, the Earth. They also shelter the scope from the computer, the power supply, the communication equipment. You can see there's a bunch of stuff on the far side of those foils from the scope, and that's the rest of the hardware. And the heat that those things give off has to be shielded so that it doesn't disturb the detector. So why Lagrange point number 2? Well, it turns out that at that point, the gravity of the Earth assists the telescope to keep up with the Earth's orbital speed. Normally, if you go farther out from the Sun, then the farther out you go, the slower the speed you go around the Sun. But because the Earth is close by, it gives you a little bit more gravitational pull, and it enables you to keep up so that you're always kind of locked in to where the Earth is. Now it turns out that the scope, it doesn't just sit at one point, but in fact, it slowly orbits around the Lagrange point It's going to take about 6 months to go one orbit as it goes around the orbits around this empty point in space. It turns out that the size of the orbit is actually larger than the lunar orbit. So it's a substantial thing. It's not just kind of moving slowly in a small orbit around this L2. It's quite a large orbit. So if we were to look at our diagram, then you would see this orbit of the Webb going around L2. So where is the James Webb located in the night sky? So what I did was I decided to find out where it would be located, not tonight, not the next week, but I looked ahead in the weather forecast, and it seems that there may be some clear skies about a little over a week from now. So I picked January the 24th, and here we are looking up in the southeast at about 8 o'clock in the evening. And here we have Orion, and then we have Sirius and Procyon. So we've got these stars to kind of orient ourselves. And it turns out that according to the NASA website, that the Webb telescope will be sitting right there on the 24th of January. And then a week later, it will have moved a little bit. So by the 31st, it's going to be sitting right there. And then on the February the 7th, another week later, it's going to be moving there. And so the 24th, by the way, is when it's supposed to have reached the Lagrange point, or at least the orbit of the Lagrange point. We're going to look at that a little more. But so this is kind of where it's roughly going to be. However, we have to remember that as the Earth goes around the sun, so the Webb telescope will continue to track through the sky. So it's not going to sit near Procyon for any great length of time. It's going to kind of march through the stars, but not just in a simple line, but in a kind of a slow elliptical orbit. So we're going to get to see epicycles in real life. So this is the location in the next few weeks of the James Webb Telescope. Well, where would we expect the Webb to be? And so I figured, well, okay, it's going to be off the opposite side of the Earth from the sun, which means it's going to be on the ecliptic, which is the apparent path of the sun around the Earth through the year. So it's the same thing as saying that it's going to be pretty much on the same plane as the Earth and the sun. So it's on the ecliptic, and it's going to be 180 degrees from where the sun is. So I looked up, and on January the 24th, the sun is at a point 306 degrees along the ecliptic. So if we subtract 180 degrees from 306, we get 126 degrees. So that's where the LP2 Lagrange point should be. So here's a picture of the sky again. This is midnight. Midnight's a nice time to pick, because that's when you can pretty much think that the sun is going to be exactly on the other side of the Earth, sort of as far away as can be. And so I've now plotted on this sky the ecliptic, which of course is just the path of the sun through the year. And I've also plotted the meridian, which is simply due south, a line that starts south and goes straight up and overhead. And then I noted that, whoa, they cross at 126 degrees, which is kind of what you would expect. And that's where L2 should be, at least in my naive and sort of simplistic way of understanding. Well, I've also, though, discovered how large, how far away that, oh, by the way, here's Procyon and Orion. So that gives us an orientation to those stars, which we've already seen. Well, the greatest distance from L2 to the Webb telescope is estimated to be 832,000 kilometers, which is actually a substantial distance. It's only 1.5 million kilometers away. And the angular difference is about that much. And you'll notice that we're quite a ways short of Procyon, which is where the Webb telescope is supposed to be on this night. So something has gone a little wrong here. Not exactly sure what, but at least we're in the ballpark. This is say an example of the type of elliptical orbit we might see the Webb doing around L2, but L2 is going to track along the ecliptic. And so it's going to change from month to month. So this would be, so we could then say that the Webb telescope is going to be near the meridian at midnight, no matter what time of the year you're looking. It's going to be looping in some sort of ellipse, and maybe they'll have better parameters on that ellipse once it settles into its orbit. And we can expect that the Lagrange point will move higher in the winter because the ecliptic will be higher at nighttime in the winter, and L2 will go lower in the summer because if the sun is high, then midnight the ecliptic is low in the sky. So that gives you an idea of where the Webb telescope is going to be 1.5 million kilometers from the Earth and going in this rather large looping ellipse around the Lagrange point. What about actually viewing it from the Earth? Well, I don't know if that's going to be possible, but it's turned out that an amateur astronomer named Ethan Gahn has actually viewed it as it moved out towards its final site. He caught it moving through Orion's belt. At this time, it was 160,000 kilometers from the Earth, so it was definitely is on its way, but nowhere near the 1.5 million kilometers that it's going to end up at. And if you'd like to see the result, you can actually just look it up on YouTube. Just type in "I captured James Webb," and it will take you to a YouTube entry, and it shows you zooming into Orion's belt, and then he shows you this little dot that tracks through that area. Perhaps once it gets out there, maybe some expert amateurs with high-powered telescopes and high-powered cameras might be able to catch a glimpse of it, but it's definitely a long ways away and it's quite small. Okay, now let's go on to the planets. January the 29th, again, it's not too, it's a little ways down the calendar from today, and so it gives us a little bit more hope that it'll be sunny. So here we have the Venus, the Moon, and Mars. So this is just after, well, just before sunup at 6:30 a.m. in the morning, and it's fairly low in the southeast sky. There's the fist that shows you roughly 10 degrees. So they're all below 10 degrees, but still with a reasonable southeast exposure in the sky, you might be able to pick out this thin crescent moon, Mars and Venus. So that's January the 29th at 6:30 a.m. Then on February the 2nd at 6 p.m., so we're now in the evening, if we look in the southwest, Jupiter and the Moon. Again, it's fairly low in the sky, and it's just after sunset. And so that's what you can see February the 2nd at 6 p.m. And then lastly, on February the 5th at 6:30 a.m., so we're back to the morning. Again, you can see Venus, Mars, and Mercury. If you have sharp eyes and there's no clouds, and you have a low horizon in the southeast, because it's going to be quite low in the sky. But any opportunity to see Mercury is perhaps worth some effort. So that would be on February the 5th at 6:30 a.m. So I've looked ahead, and Seashell should have some cloudless skies in a week or two. So unless the forecast changes, there's some reasons to be optimistic. And I hope to see you on February the 12th for our next meeting of the Sunshine Coast Astronomy Club. So that's it.
So this sketch shows the approximate orbit of the James Webb in halo orbit around the L2 Lagrange point. And you notice there's a straight line between the sun, the Earth, and L2. And this geometry is maintained as the Earth and the L2 point go around the sun. So the Earth and the L2 point both have a solar orbital period of 1 year. And the James Webb is in pseudo orbit around the L2. It's not a real orbit because it's not going around a gravitational body, and it's not repeating itself. It's kind of like a messy ball of yarn, the path that it follows. And it's not really stable because it's kind of balancing there, but it's an unstable equilibrium. It's kind of like if you imagine putting a basketball on top of your head, you can balance it there, it's in equilibrium, but you have to keep on wiggling to maintain it. And the James Webb is the same way. It has to have little tiny orbital adjustments every few weeks just to keep it in that sweet spot. Otherwise, it'll fall off its kind of little gravitational hump that it's on. And the two directions that it will fall is either towards the Earth or away from the Earth. And it's because it has this tendency to drift, it has to have a rocket that can push it back into position. The rocket can only point towards the sun. You can't have a rocket on the cold side of the James Webb because that would really mess up the telescope. So the rocket can only push in one direction. And unfortunately, that's the same direction that the solar light pressure is pushing against the sunshade. The sunshade acts like a giant solar sail and is pushing the James Webb away from the sun. And if it pushes it beyond L2, then it just keeps on going and there's nothing they can do about it, and the telescope's lost. So when they inserted it into the orbit, they inserted it into the orbit a little bit too close to the Earth so that it has a tendency to fall towards the Earth instead of falling away from the Earth, and the rocket can keep it in place. Another aspect about it not being in orbit is a regular orbit. The restoring force that attracts the satellite to the central body is gravity, and that falls off with the square of the distance. There's no force that's falling off with the square of the distance from L2 to James Webb. And this orbit acts more like a simple harmonic oscillator than a Keplerian orbit. And because it acts like a simple harmonic oscillator, like a pendulum, it always has the same period regardless of its distance from L2. So if it does start spiraling in towards L2, it'll have exactly the same period. And the period happens to be 6 months or a half a year. So James Webb goes around L2 twice for every time it goes around the sun. The shape of the orbit, this oval, was chosen to avoid eclipses, and not so much from the Earth because you'd have to be right at L2 to be eclipsed by the Earth, but to avoid eclipses from the moon, because the moon's orbit is not shown on here, but it's in the same plane as the Earth's orbit. So, and if you extend out the potential danger zone fits inside this this oval. I'm not quite sure why they were so adamant about not tolerating eclipses, because the L2 point is way beyond the Earth's umbra, so there's no way that the Earth could completely block the sun from the solar panels, and the moon even more so because it's even smaller. But that was a criteria that NASA settled very early in the design process. So if the fuel holds out, then James Webb should be able to maintain its position for at least 10 years. And they think it's got enough fuel maybe for 20 years, which would be absolutely phenomenal to get these potentially fabulous pictures for 2 decades. So there you go. Any questions about this? That business about the simple harmonic oscillator, I just had to stick it in there because that was something that I actually worked out when I was trying to develop an intuitive understanding of what the hell is going on with these halo orbits, because they obviously just break every single rule of orbital mechanics that we're used to from playing Kerbal Space Program or something. I mean, like, it's at right angles to the plane that it's supposed to be in, and it's not the right shape, and there isn't a gravitational body and all this. Well, the restoring force is the balance between gravity and centrifugal force. And before Bruce jumps in to point out that centrifugal force does not exist, and of course it doesn't exist, if you're analyzing it in a rotating frame of reference, as if you're like standing on a merry-go-round, it's really hard to believe that it doesn't exist. And the mathematical analysis of the Lagrange points always use a rotating frame of reference, and the Coriolis force, which is another imaginary force that doesn't exist, and the centrifugal force are kind of essential for understanding what's going on with them. Oh, and if you consider it a simple harmonic oscillator, a pendulum that's the length of the distance from Earth to James Webb, and use the high school formula for simple harmonic motion, you get a period of 6 months. So it's not correct, and I'd get thrown out of an astrodynamics program, academic program, if I proposed it, but it actually works as a first approximation.
Thank you very much for that.
Love to think about that.
Yeah.
Just the thing.
So that means that the location, the expected location for Webb in the night sky is even farther from where I would anticipate it would be. First of all, because the ellipse is centered on L2, but it's also, you should basically lined up so that the major axis is in the direction of the ecliptic. The minor axis is perpendicular. So I'm very puzzled then. Either I don't quite understand where L2 is, or something's odd.
Well, you're right about L2. L2 is at the anti-solar point.
Yeah, okay.
But L2 doesn't exist. Another one of these things doesn't exist, and it wanders around, and it's pulled by different. Jupiter pulls it this way, and the moon pulls it that way and stuff. So besides not existing, it doesn't stay in the same place. But the oval of the halo orbit is the major axis is in the ecliptic, and it's about a 2.5 to 1 aspect ratio of wideness to perpendicularness.
Okay. Oh, this is good. This is a good, that whole presentation is just a great add-on, and it kind of, even though it contradicts what I said, at least it leaves the person with a better understanding, which is great. Great.
If you give me another year, I'll figure out the L4 and 5 points, because they're just a complete mystery to me.
Okay.